All right, so welcome to the virtual class. So what I'll do is basically we're just going to go through the nodes, and I'm just going to point out things on the nodes and just talk through it. I have the guitar here, so we can demonstrate a couple of things. All right. So where did we get to in the before time? Well, in the before time, we really got to the bottom of this page. This is was the last page on the set of notes that I posted, and we got to this equation over here. So this was, we had the guitar string was trying between the bridge and the nut, and it was looked something like this, where the displacement was y, the position on the string was x, and then there was also time. So y is a function of x and t, and so at each position it can have some displacement, and of course the displacement is going to be different in different time because the string vibrates, right? And we're trying to figure out how does it vibrate. So the equation that we got for y that it has to satisfy is this thing, and it has t was the tension, and rho is linear density of the string, right? So how many grams or kilograms or whatever your favorite unit is per unit length, right? How how heavy the string is. So all right, so we have this this equation, right? And let me go up here, right? So this is called the wave equation, and it's really, I guess you could say that it's the sort of the most important equation sort of in the universe, right? I mean, that's the equation that the universe behaves by, right? That's the most fundamental equation in some sense. It's called a PD, or a partial differential equation, because it's an equation in partial derivatives. So it's not really saying, it's not quite a differential equation. It is it's sort of the most complicated of all differential equations, the partial differential equation. The one that we got for harmonic motion was just there was just a derivative in one variable. So it was a so-called ordinary differential equation. You can see that people that came up with this terminology didn't really must have not liked differential equations, right? Because, well, it's either you have partial differential equations or you have ordinary differential equations, right? And neither of those sound very exciting, right? Okay, well, let's look at where some of the the last parameter that will be interesting comes in, and that's this L, this length, where that's the length of the string, and that doesn't seem to appear in the equation itself, right? But where it does appear is that maybe we can show it here, right? It's the string has to be held at a fixed position at the beginning and the end, right? So we have to somehow represent that, right? It's not represented in the equation, and the way that we represent that is there's two extra equations. These are called boundary conditions or side conditions. It's basically saying that at every time, no matter what time is, t can be anything. If x is 0, then the displacement is 0. The string is not moving. Maybe I can, right? I mean, over here, the string is just fixed on here, right? It's not moving up and down, even if the rest of the string is moving, right? It's fixed at this point, right? So this is the 0, right? And this is where the L is, right? It's the length of the string, right? So we have whatever solution that we want should satisfy these two conditions. Now, the way that let's just talk about the units for a moment. The way that we'll write the equation is really like this. Or the way that people write this equation is like this. And so we've really, just rewritten that before. This was the c squared was t over rho. It's tension over the linear density. So c is of course the square root of that, right? Or maybe the square root of tension over the square root of rho, however you want to write it. So this c, sometimes people call it the speed of light, and it really is a speed. It's going to be the speed at which the waves are propagating. And to see that it really is a speed, the best thing to do is to look at the units. So what are the units of t, right? T is in newtons, right? What are newtons in the, it could be different units, but if we're using the standard SI units, right, the MKS units, it's the forces are going to be given in newtons. So the newtons are kilogram meters per second squared, and rho, well, if we are using an MKS, the linear density is going to be in kilograms per meter, right? So if we look at what the units of t over rho are, this is t, this is rho, right? So we write down the units. We get the kilograms cancel. The s squared goes on the bottom. The m over here, if you work it out, goes on top. So we have meters squared per second squared, or in other words, maybe I'll write it over here like this: meters per second squared. Well, it's c squared, right? So c is in meters per second. So it really is it's speed, right? It's speed in the MKS units. All right, so now that we know what c is, let's just ignore it for for a while. Because to figure out the solutions, it's best to simplify things. So we're going to assume that c is 1 to figure out the solution. So we really have this equation. And another simplification, we could set L equal 1, but it turns out it's almost simpler to set the length equal to pi, right? So we're going to have a guitar, not this guy. This is actually not a guitar. This is a baritone uke that I stole from Jay, and it's not the length of the strings is not pi. If pi meters long, it'll be a very, very, very long uke. Slightly longer than a regular ukulele, but it's not pi meters long, right? But maybe you have a guitar that's pi meters long. So there's going to be our L. So that means that our one of the side conditions doesn't change. It's just that the other one here we're setting L to be pi, right? So we're trying to find functions y that satisfy this, and this, right? And it's gonna tell us how the guitar, what sound is coming out. So, all right. So again, we can think of functions whose derivatives are sort of kind of the same thing, and so we get again to sines and cosines. Let's just think sine. Well, if we take two derivatives of sine x, we get minus sine x, and if we take two derivatives of sine t in terms of t, we get minus sine t. But also we have that if we plug in x equals 0 and pi, sine x, sine of 0 is 0 and sine of pi is 0, right? So if we try a solution of this form, sine of x times sine of t, then presumably it should work. Well, let's it's always good to check these things. So we have first, let's figure out the boundary conditions. So we plug in 0, and yeah, it's sine of 0 times sine of t. Well, sine of 0 is always 0, so it's 0, right? So y at 0 and t is whatever is always 0. Similarly, if I plug in x equals pi, right, because sine of pi is 0, right? So the whole thing will just be 0. You find the next page. All right, here. So the boundary conditions work out. So let's figure out the what do we have about the differential equation, right? So we have the second derivative in x. Well, if we take the second derivative in x, nothing really happens to the t, right? So sine of t is just a constant if we're taking a derivative in terms of x, right? So it's really, y, remember, if I'm not, we have it on this page as well. What was y? It was sine x times sine t, right? So it's really, if I'm differentiating in terms of x, it's almost as if the sine of t was just a constant, right? It doesn't interact with the derivative. So when I take the derivative with respect to x, I will get cosine, and then I will have minus sine, right? So I have, if I take two derivatives with respect to x, I get minus sine x sine t. And actually I get the same thing with t. If I'm differentiating with respect to t, the sine x is just a constant, right? And I'm just differentiating the sine of t, right? Okay, so if I do that again, now I'm sort of I'm putting a negative basically on the second term, but I still get the same thing, right? So that means that this thing equals this thing, and we have a solution to our differential equation, and it satisfies the boundary conditions as well. Now we could, that's one solution. We could try cosine instead of sine, because not for the x, because we need the boundary conditions to work. But for t, we could instead of sine t, we could put in a cosine t, and you can check that still works. But it turns out it's it gets us something, but we don't necessarily going to worry about all the possible solutions that we'll get. This just the sine will actually give us enough to work out what's going on. So let's ignore the cosine, and one way to say that we're going to ignore the cosine is by giving this this condition as well, which really says that's the simplest extra condition that I can put on there. It basically says that it's the initial at time t equals 0, the string is perfectly straight, right? So it's not quite what happens when you pluck a guitar. That's when you change the initial shape, rather than here we're only going to be changing the initial speed. But it's good enough, and it's going to be it's going to give us simple looking solutions. So anyway, so that's basically what we're doing. At time t equals 0, the string is perfectly straight. It's not again, it's not a big deal. Don't worry too much about it. The what we do want to worry about is what other kind of solutions we get, not by changing sine of t, but let's try to change the sine of x. Now, we can't make that a cosine because we need it to be 0 when x is 0 and when x is pi. So sort of stuck with sine. But if you notice the way if I have a sine wave, right? If I make the sine wave go twice as fast, right? I get something like this. This was the graph of sine of x, and this is the graph of sine of 2x, right? Now, the thing is that if I look at sine of 2x and I plug in pi, I still get 0. Sine is going to be sine of 2x is also going to be 0 over here. It's also going to be 0 at x equals 1/2. Well, who cares? It's going to be 0. Sorry, 1/2 of pi. It's going to be 0 at 0 and pi, right? So this is, you know, if I want to draw the axes, right? This is where you know, where things are. So okay, so we have this thing. Well, we can do the same thing with 3x, right? Because sine of 3 pi is 0, sine of 4 pi is 0, right? So we can take any positive integers, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to you know, all the way to infinity. Well, you can, you know, this is going to be really the frequency, so you don't really have to go arbitrarily large because, well, we won't hear the large frequencies anyway. But you know, if you want to go from 1 to 100, it'll be way more than enough. So this you know, we get that sine of 5 pi is 0, sine of 10 pi is 0, sine of 100 pi is 0, right? So this is sine of n pi is 0 for all integers n, right? So we want to try sine of nx. Now, that's not going to quite work out here if I just change this. Or, sorry, if I just change this, right? Because when I do the derivative over here, I'm going to get an n squared coming out, right? So what we have to do is we have to change the t part as well and stick an n in there too. And that will actually work out if we basically replace it by sine of nx times sine of nt. That works. Let's check the boundary conditions, because if I have at 0, well, just n times 0 is 0, so that's just 0, that's fine. The other boundary condition is sine of n pi, right, and that's again 0, right? So again, we're satisfying both boundary conditions. Now, let's differentiate. If we differentiate, sine of nx twice, right? And that's going to be minus n squared sine of nx, right? So I'm going to get, I get an n squared out here, right? Well, that's the same thing I get from the t derivative, right? I again get the sort of n squared and the minus sign, of course, right? And so I have that this is equal to this, therefore this is equal to this, and we have a solution, right? So this is a solution for any n, right? Now we could multiply by constants. That's going to make things louder, right? We could say 3 times sine of nx sine of nt, right? You know, or anything, you know, any number over here, right? For all of those, it still works, right? So so we have all of those, and this equation, this equation that we're solving is it's linear. and that means that we can add solution. Let's not worry too much about it, but yeah, you can. If I have two solutions, I can add them together. Sometimes, in more fancy language, if you superimpose two solutions, and that's basically running multiple. It's things going at multiple frequencies. I mean, the simplest way to superimpose is to maybe maybe play two different strings, right? But we're only worried about one string. But there's actually infinitely many possible frequencies on the string. So. So, for example, this complicated expression is again a solution, right? Because it was when n was 1, and I maybe took 0.7 times that. I took 0.5 of this guy. I took a quarter of this guy, right? That is a solution, right? That gives me a solution that gives me what the guitar does at some particular point, right? Now, most generally, what we get is I don't know if you guys saw this symbol before, but it just means it's an infinite sum. So the most general solution is basically it's a sum like this, right? And it's this sort of magic ellipses, right? It just means it goes on forever, right? That's why there's this infinity here. So you have basically I can take any constant over here. I'll call it B1, B2, B3, B4, B5, and so on. And I'll just so that's basically the B1 is the coefficient of sine x sine t. B2 is the coefficient of sine 2x sine 2t. B3 is the coefficient of sine 3x sine 3t, right? And these are just some numbers, right? They're really going to be the contributions from the different frequencies into our sound, right? And if we allow that cosine in there, we just get a slightly more complicated thing. That would be a phase shift on every on every one of these signs. But let's not worry about that. For our purposes, this is going to be good enough. It's sometimes called a Fourier series. It's basically what it's doing. It's taking it's writing a signal, and the signal is the sound that you're hearing, and writing it in terms of its component frequencies. Right. This is, for example, what a radio does. You have the antenna, and it's getting all these. Normally you could get all possible signals, but you have to pick out that one particular set of frequencies, right? That's when you're tuning the radio, you're tuning to a different frequency, and it wants to pick out just what's over there, right? So it's using something like this, maybe not for a series, for a transform. It's all these things where the name Fourier appears. So okay. Let's go over here, and now there's an interesting thing that I find really wild, and I don't know, not too many people seem to find it as wild as I do, but I find it's really interesting. It's the fact that if I have a guitar string, right, that the what it does in time is basically the same thing as what it does in space, right? So if you want to think about what's the shape of the wave that you're hearing that's coming into your ears, what's the shape of that wave, right? If you'd want to sorry, it's not coronavirus, don't worry. Just allergies. If you want to figure out what does that look like, what would that look like? Well, you can look at what the shape of the string is, or vice versa. If you want to get a certain sound, you could try to mimic that shape of the string. Now, maybe let me put this onto the guitar. Now, so that means that we could basically get sort of any sound whatsoever from a guitar if we just had the right pick, right? Complicated enough pick for the guitar. It's interesting that it can basically emulate any sound whatsoever. Now, of course, it's hard to pick more than a couple of different sounds, but it's definitely different. For example, if I take my thumb and I don't use any sort of sharp bits of my thumb and tongue. I don't think you should lick the guitar. Not in these times. I think, although it's just been under my desk, so maybe there's no viruses on it. But still, probably Jay wouldn't approve of me licking his guitar. So if I take my thumb, where's my thumb? And I'm gonna do it just in the middle, and I get sort of a nice mellow sound. There's not too many high frequencies over here, but if I do it with a sharper bit, there's definitely, it has a different sound. I don't know if you can hear it, right? But there's sort of a little sharper sound. But that's if I'm doing it in the middle of the string. If I do it all the way at the end with something, with a fingernail, so getting fairly sharp sound, I definitely get a very different sound than. Right? So, and that's really because when I do it with a fingernail and very close to the bridge, I'm basically getting close to that sawtooth wave that you saw on the website, right? So that's basically the way this works, right? So what we're getting is this is basically all the different frequencies, all the different overtones. We get the bass frequency, and we also get other overtones. Now, one way that you can sort of emulate just the overtones is, well, we could maybe, in here I could hold my finger very lightly in the middle, right, and that's gonna mute that first term, the term was the sine x sine t, and I just get basically twice that frequency, right? It sounds a little different than if I do this, if I fret the string over here, if I make the string half the length, but this is, I'm just zeroing out all the well, mainly I'm zeroing out the fundamental frequency, the first guy, the sine x sine t. That's called the fundamental. That's really that's where the name of the string will come in, and also that's sort of the frequency that you hear. But there's all these other overtones as well. Sorry, my computer just turned off the screen, so I was worried that it stopped recording. But there's all these other frequencies. Let me go back to the notes. Right? I mean, we have the fundamental frequency. We have twice the fundamental, so that's an octave up, right? This is those octave and a fifth, right? But you don't just get these; you get all of them. You get 4 times, so two octaves up, 5 times, 6 times, 7 times. You get all of these guys. Now, what's interesting, just to sort of tie it back to the tuning part of the course, was that what we're getting, even though the guitar is tuned with equal temperament, so that's where J, I guess, ended, right? That was that's our current tuning. So all the frets and everything is figured out so that it's equal temperament. But the overtones on each string are actually not equal temperament, right? They are actually those pure nice multiples, those multiples that where J started with, right? This 3 times up, right? That is actually that's the real. If this was C, then octave up would be that would be the C octave up, and this would be the G in the next in that next octave, and that would actually be really 3 times that frequency. But if I'd play it on the guitar using a fret, that wouldn't be, right? So playing it on the guitar, well, I just get the G in the playing it with a different string using the frets. I would get the G in the equal temperament tuning, but in this so-called harmonic series, right? I get all the nice pure multiples of the frequency. So that's also kind of interesting that sort of tells you how a guitar is going to sound, because you're gonna when you play different strings, you're sort of mixing both equal temperament and and actually all the different things in the harmonic series, right? So it's all the different just pure multiples, right? So that's kind of an interesting thing. It also tells you something about why does it sound the way it sounds, right? Okay, so let's so we're basically right over. Where did we get to? We basically got up to here in the notes. So I'll post that. And I guess this took maybe a little less than it would take in the lecture, but well, it's in the lecture I have to write everything down, so it would this would definitely take the entire lecture if I was doing it on the board. So we'll end here, and then we'll do some more next week. All right.